the technology that I'm going to be talking to you about, all of the technology on the nanoscale is within the width of a single hair. Basically, this device is extremely thin, and this is the future in terms of our technology. She's able to open it up. You can literally see through this device. It is amazing. So think of your iPad, but think of something a million times better than that. She's wearing it on her wrist. So you can open it up and you can fold it. And this is a very new type of technology. It's called flexible electronics. Touch screens. The device is incredible. Multimedia, does everything. And this is what I was telling you about. This is the new technology, the so-called stretchable electronics. And you'll see that there was a bit of material system which was bending. And this is called a graphene, which is a single atomic layer of carbon atoms. And you can be very proud in the UK, in 2010, the Nobel Prize was awarded to two physicists at Manchester University for their work on this amazing material called graphene. And because it's so thin, it will open up the door to all of this amazing technology. Oh, you can even buy your groceries with it. And of course, if you want, you can watch a movie as well. What actually can't it do? Now, who wants one of those? I do. Yeah, okay. So we're in the process of trying to make this technology.
So quantum computer is a tremendously fast computer, a computer of unimaginable speed. So just to give you an example, I mean, certain problems a normal computer would take 1 million years to calculate, a quantum computer could solve in a few milliseconds, in a few fractions of a second.
It was Richard Feynman who pointed out that no classical computer can ever perfectly mimic a quantum process. And quantum processes include things like chemistry, which is all about quantum physics. So when we have a quantum computer, we will be able to make computer models, very accurate computer models, of processes involving chemical reactions, up to and including biological reactions. We will understand much better how proteins work, how genes work, and that will have tremendous implications in developing both the chemical and the biochemical technology of the future.
Quantum computers are completely entirely different to normal computers, and they're relying on a theory called quantum physics. And quantum physics is very, very strange, very strange effects. And Einstein, in fact, called it spooky. So one of the things which happen in quantum physics is superposition. In superposition, something can be at two different places at the same time. So an atom can be here and over there. I can be standing here and over there simultaneously. So what we do in quantum computing is we try to utilize superposition. And so we make atoms being in two different places at the same time. Now let's go back to what a normal computer does. A normal computer has bits, and these bits encode information. So numbers and words, all of these things are just encoded into bits, which are a bit is 0 or 1. And so basically information is just written into a string of zeros and ones. In a quantum computer, instead of having bits, you have quantum bits. And so these can be in a superposition of 0 and 1. So they can be 0 and 1 at the same time. When basically solving a problem in a quantum computer, we can have all the inputs of the computer simultaneously, rather than having one input, then another input, then another input, and calculate these things one by one. All the inputs coming simultaneously are being encoded into a quantum superposition, into a quantum bit. And so now this quantum bit is then computed, and we get all the answers out at the same time. This is what makes a quantum computer very, very different to a normal computer and unbelievably powerful.
So if you've got 10 switches in a conventional computer, that's a 10-bit computer. If you have 10 switches in a quantum computer, they're called qubits, you have 2 to the power of 10, and that's just over 1,000. So you've got a kilobit instead of 10 bits, and that's just the very beginning. That's where people are now. Imagine what happens when we've got 100 qubits in a computer.
Here at the University of Sussex, we're building a quantum computer using trapped ions. Ions are charged atoms. And what we do is we actually cool these ions down nearly to absolute zero, so to minus 273 degrees Celsius. And then we take these ions and we manipulate and we encode information into the ion. Now, the ions are actually trapped inside a vacuum system, and you can see that over there. Now, if you go on a space shuttle and you step out of a space shuttle in outer space, you have much more air to breathe than inside one of these vacuum systems. So it's literally, there's absolutely nothing in there. And then basically, using electric fields, we actually hold an ion and we can then trap that ion using electric fields, and then we use laser beams to cool that ion nearly to absolute zero.
This protein folding problem, as it's called, being able to go straight from the underlying sequence of the protein to the three-dimensional structure, is one of the holy grails in molecular biology. And some approaches have been made to it, but the complexity, the numerical complexity of it, and the whole simulation problem has really stymied a real solution to that problem. And that's something where much more powerful computers would really help.
The bottom is where the ion is in one state. The top is where the ion is in a second state. And as you can see, we're going between the two states, and here is the point where the ion is in both states equally at the same time.
And if it's going to cost you £10 million to predict the drug that was going to work, rather than £1 billion to actually develop the drug that's going to work, I think drug companies would go for that.
Hello everyone. Thank you so much for inviting me here. The city is absolutely beautiful. I'm going to tell you about cyborg anthropology and the evaporation of the interface. I only have a little bit of time, so I'm going to go into it pretty quickly and give some examples. So first off, whoever has a cell phone, hold it up right now. All right, those who held it up first are more cyborg-like than the others in the audience. In fact, we're all cyborgs, but not the type of cyborgs that you think. We're not RoboCop or anything like that. A person called David Hess talked about the idea that we're all low-tech cyborgs, that every time you look at a screen and you interface with something external to yourself that holds information that your eyes can interact with, you're kind of a low-tech cyborg. Even though it's not melded into your skull or interacting directly with your brain, it is interacting with you through an interface of your eyes or your hands, and therefore you're a cyborg. So the term cyborg came from a 1960 paper on space travel. It was called An Organism to Which Exogenous Components Have Been Added for the Purpose of Adapting to New Environments. Basically, this was talking about an astronaut in space, because what kind of a hostile environment is space? It's very difficult. You can't breathe out there. So the idea of making a spacesuit was allowing somebody to evolve outside themselves to adapt to this very difficult environment. So the first tools extended the capability of our fists. So the idea of having a hammer or a knife allowed us to have an external tooth or an external fist that we could evolve outside of ourselves as a physical extension of self, to be much better than we could be as actual humans. But now we have these mental augmentations, allowing us to store our memories on our brains and our essences in these devices. So Maureen McHugh said soon that perhaps it may be impossible to tell where humans end and machines begin. When you look at your online profile, is that really you? Is a representation of you that can be acted on when you're not there. But where do you end and a machine begins? The thing is that humans and technology have co-evolved with each other over time, being very, very co-creative. We have survived because of technology, and technology has survived because of us. So a traditional anthropologist goes out to another country and looks at the natives and says, how interesting their cultures are, how curious their techniques, look at these tools and these customs. And it's all very much that the anthropologist is an other person, and they go back to wherever country they came from and talk to people about these interesting people. But the cyborg anthropologist looks at the world around them and says, how curious these people are. They have these little devices in their pockets that cry, and you have to pick them up, and you have to soothe them back to sleep, and at night you have to plug them in and take care of them. And then every 2 years they break down on you, so you have to get new devices. So these Macy meetings started in 1941, and they were about a bunch of scientists and anthropologists coming together, realizing that technology was going to be an extremely big deal in the future, and they tried to convince a bunch of people of this, but it was very early on. Mainframe computers were barely getting a start. So it took until 1992 for cyborg anthropology to be an actual subsection of the anthropology of science. So let's talk about the present day. So in the present day, we have these devices outside of ourselves, and they help us to communicate with each other. But also, we're carrying around these devices that are larger on the inside than they are on the outside. So whenever you carry around a laptop, it has all this space inside of it and all this space connected to the cloud, and you never see it. Whenever you put a file in a system, it doesn't make your computer heavier. Although if you put a file in a file cabinet, it would make the file cabinet much heavier. So if you were to take your 8 years of pictures that you stored up in a laptop and actually print it out, this is what it would actually look like. This was a campaign for Maxtor hard drives where they printed out 8 years of somebody's photos. Because it's easier to put something into a space than it is to take it out. So we're carrying around these kind of Mary Poppins bags where we can take anything out that we want. So when you start putting memories into a computer outside of yourself, you start to have these hyperlinked memories. And what happens when you have hyperlinked memories is it's not just thinking in your brain, oh, where did I put that memory? And you try to think of a word to trigger the memory. You have to actually think of a word to trigger a memory. So, for instance, on your email account, if you want to find an email, you have to actually type that word instead of just think about it in your brain. And that makes us into these kind of persistent paleontologists, digging through all of our old data, trying to find out, the thing that we left there that's been buried by hundreds and hundreds of emails. So we're all becoming this kind of paleontological machines that are going out and digging through everything all the time. And if there's too much of that, and too much sediment gets laid down, and too many emails, we start to have these kind of panic attacks. There's too many emails, there's too much information coming in. So this brings me to the idea of prosthetics and their discontents. We have all these external prosthetic devices, and actually Freud wrote this book called Civilization and Its Discontents, and he warned of this future in which we would have ill-fitting prosthetics that were pretty good, but they weren't all the time good, and so we kind of, as humans, live in this mild dystopia. It's not a complete dystopia world, because if it was, we'd get very angry and revolt, but it's just mild enough that we have some complaints. So whenever you have a device and it freezes up on you, your external brain freezing up on you, it's a big problem. One of the other problems is that your external brains last much shorter than your actual brain does. So it would last only for 2 years, and then you have to throw it out. And it makes big piles of junk. I mean, humans are very curious creatures. They have all these external objects, and they shed them, just like leaves of trees. But when a tree sheds its leaves, it makes room for new trees. When we shed our technology, it makes room for more technology. And the planet also has a bunch of junk around it. There's about 8,000 satellites up there that you can see on Google Earth, and only 600 of them are currently working. But these allow us to connect to each other and talk to each other. So even our own planet has become a cyborg. The other thing is that humans tend to make these kind of snail-like creatures that they drive in, and they're completely disconnected from each other when they're driving down the road. They're kind of like spaceships. You can't actually walk on a highway because you'd get run over by a car. It's only for, kind of advanced cyborgs that want to extend themselves and go very fast. But the problem is that when we're stuck in cars, we're kind of like on pause. We're machines, and we're not able to talk to each other even though we're having the same annoying experience of being in traffic. So when the cell phone came out, it started connecting people in these isolated environments. It started giving people something to do when they were on pause, when they were hanging out in airports, when they were hanging out in these non-spaces, where there were no friends and no family, where they kind of felt like machines. In a way, it allowed them to be more human. So there's this idea of ambient intimacy that it's not that you're connected to everything all the time, but you always have the ability to connect to someone. And if you were to look at all the people on your phone right now, it would probably look like this. All the people that you have access to right now in the tiny machine that you hold in your hand, via email, via Twitter, via Facebook, via any of the other social networks that you have, via your phone. It's like a tiny village in your pocket that you're carrying around all the time. And even if you're in an isolated place, you can suddenly reach out and have contact with somebody. So let's go into becoming a cyborg. So now kids have a kind of second self before they're even born that they learn to deal with. But this self becomes more important than your DNA. And so people are going to grow up in this world where this can act for you when you're not even there. People can click on you, your secondary self, your online presence, without you being there. So you have this ability to construct whatever you want it to be. And just as you have to, wash your hair in the morning and look presentable, you have to do the same thing with your digital self. There's a lot of people who forget to update their online status, and they feel guilty about it, and they say, oh no, my status is old. And they keep worrying about their online presence and what it looks like, and this is going to become increasingly important, your presentation of self in digital life. So as you become more of a cyborg, the delineations between work and play become more difficult to define. So reality is not always fun. You have to wait in line, and you have to wait in traffic. You're put on hold a lot. You're doing these very annoying things that humans shouldn't be doing. And sitting there in environments in which humans shouldn't really be in. But suddenly there's this layer on top of reality where you can check in and you get a few points. And you can rate reality, and you can make it so that you can have a good experience next time. And the other thing is that you get accelerated rewards. Say you get 4 years in college and you get out, and your reward is graduation. Say you want a promotion, and it takes you 6 months to a year to get a promotion. If you play Farmville and you click on something, you get an immediate reward. You get either some sort of point bonus or something that makes you feel like there's an interaction. And for a lot of people, the rewards in real life are slower than the ones online. So they're more attracted to these interfaces. And the other thing is, if you're living in a small apartment and you don't have much room to do something, you can be powerful in these environments and actually do something. It's kind of a freeing thing to do. So basically, these are kind of database games. So Foursquare is not an app, it's a data entry game where you're entering place data and you're marking territory, just like a dog going to a street corner and marking their territory, and then the other dogs can see where they are and whoever is the top dog. So if you check in on Foursquare enough, you become the top dog as well. It's a very basic animalistic game. But the whole time, this free service is collecting data about places. It's become one of the most powerful place databases because it's put this little layer on top of reality and made it fun to do data entry. And now people are just doing data entry all day for Foursquare for free. It's the same thing with Facebook. Facebook is basically a spreadsheet game. Spreadsheets have never been so interesting. You log in and it tells you what happened in column A2 and cell 4B, and then you change cell 3, and then it gives you points, and then somebody says, oh, I really liked that, and suddenly you have this psychological feeling that you're actually worth something. And it's not that you would have 15 minutes of fame in your lifetime, but 15 minutes of fame every day, and you have to keep getting that in order to feel human and connected. So social grooming becomes this very important aspect of it, that when you post something, you expect a response, and you expect to be interacted with. And if you don't, it feels physiologically bad. And because our brains are very good at mapping onto these external spaces, we can actually feel these psychological and physiological effects when we're dealing with these virtual spaces. This is virtual reality. It's 2 dimensions, but it's just as good as having a 3-dimensional virtual reality with its effects on your brain. So work is just badly designed gameplay, and I think that in the future, work and play will begin to merge more and more and more. So let's talk about the future very quick. So what will happen in the future? Well, Mark Weiser at Park Research came up with this term called calm technology. And the idea behind calm technology is it gets out of the way when you don't need it, and when you need it, it comes back into play. And the other thing is that actions, just your everyday life, moving around, will trigger events. And basically these invisible interfaces will allow you to just do something and something else will be triggered, instead of having to physically press a button or mouse over to something and click on it. Just you living will cause these events to happen. So here's an example of calm technology. When you go to the tap and you get a glass of water, it will show you what temperature the water is. You don't have to put your hand under it and get burnt or feel that it's cold. And it only turns a color when you're actually using the faucet. So it's actually a very useful piece of technology. So this is an example of some calm technology. So information should be pushed to you. And you shouldn't have to go out and get it. So the idea behind this is that when you get to an airport and you need an address of the place you're staying, it should come up and be pushed to you just on your device. You shouldn't have to be a digital paleontologist and go and dig for it under the 50 other emails that you got. It should know where you are, what you're doing, and push that information to you. So the idea is that the robots on the other side are doing what machines do best, leaving you to be a human and do what you do best. So ambient user input is a way to do this based on your location, based on your location history. Do you drive or walk more often? Based on the time of day, based on the prior actions or whatever you do on a network, can determine what to send to you. Also, instead of waiting for somebody at the corner of the street when they're going to pick you up, you should be able to see them in real time arrive on your phone. Because there's all this uncertainty around the simplest of things, which is meeting somebody, right? You don't want to just wait for somebody for 20 minutes. But if you knew where they were, you wouldn't have to text back and forth saying, I'm going to be late, I'm on my way. Oh no, I got stuck in traffic. Oh, I just left my house. Oh, I'm 5 minutes away. Because by the time that happens, somebody's around the block getting a bagel or something. Also, geo-notes. So the idea of a location-based reminder that you can leave your grocery list at the store and forget about it. And when you get to the grocery store again, get that list sent to you. Something as simple as that in everyday life, just getting helped out by technology so you can store it and forget it. Your brain doesn't have very good, it doesn't float contextual memory. It doesn't say, okay, I remember that I need batteries now because when you get to the store, you need milk and you forgot the batteries and you get home and your flashlight never works, so you never get the batteries that you need. So leaving something in a location allows you to leave a message to your future self. So the idea is that your mobile phone is not really a phone. It's a set of sensors, and these sensors are a miniature wearable computer that you have with you all the time. And there's a server up there that can compute things for you and send back information to you. It has GPS, it knows the time of day, it knows how fast you're going. And this should be able to compute things for you and become effectively a remote control for reality. So for instance, I have this set up in my house. When I get home, it automatically checks me into my house because it knows that I'm home. And then it triggers the lights to turn on. And then when I leave, it triggers the lights to turn off. And I never had to press a button the entire time. Just me being there has triggered an invisible button. So I didn't have to press anything. I didn't have to turn on the lights or remember to turn off the lights. And that's one action I don't have to remember anymore. And that's something that frees up my mind to think about other things for a few seconds a day. So the best technology is invisible. It just gets out of the way, lets you live your life. And so the idea behind interfaces is that the first interface was these big buttons. And if you wanted the buttons to do something different, you'd have to physically rewire the entire device. But when the interface became liquid on a screen, you could use software to reprogram those buttons. So it goes from solid to liquid to air. So the next interface revolution is this air, just doing things and having things happen, which is the idea behind ubiquitous computing, which is finally capable of being done because we have the internet and we have this whole database up there that allows us to compute in the air and send it to devices all over the place. So the idea behind cyborg anthropology is to look at what's going on in the world, step outside of culture and see what's actually happening with these weird devices in everyone's pockets and see how that affects culture. So thank you very much.
When I joined Intel, Intel was a memory company. they had never designed complex random logic circuits. My major contribution was to figure out a way to integrate all the complexity of a CPU into a single chip, which had never been done before. The biggest value that the microprocessor brought to the world is to be the core element of the information revolution that we are in the midst of. In that sense, the microprocessor is similar to the engine. And the engine was the core of the industrial revolution that has characterized the last couple of hundred years. The engine extended the muscular power of human beings and thus enabling the industrial revolution. The microprocessor extends the intellectual capacities, the brain power of human beings, thus extending the human reach into areas that an engine cannot. What is the future of computers, and will they challenge human intelligence? Well, in the future, I see, of course, more of the same, faster, cheaper, more power-effective microprocessors and microcontrollers, of course. But the new defining object of the future may well be quantum computers. Quantum computers, which today are still not a reality. They're being studied in many universities and research centers. But they promise to change in a fundamental way the nature of computing by allowing to compute way beyond what a mechanical computer like a traditional microprocessor can do. As for whether computers, whether quantum or not, can rival human intelligence, I have my doubts. I think that human intelligence, of course, in the lower manifestations of it, will be aided tremendously by computers. But there are aspects of human capacities that have to do with intuition, with will, with intention, with imagination, with creativity. All those aspects, I don't believe any machine can really replace. And in that sense, the machines will be quite helpful because they will allow human beings to recognize what makes them human and will recognize how more powerful a human being is than a machine. Since I retired from business a couple of years ago, I have started a non-profit foundation for the study of consciousness. Consciousness, in my way of looking at, is the new frontier, is what defines a human being and distinguishes it from a machine. Consciousness is the ability that human beings have to experience, to think, to know that they know or to know that they don't know. A machine cannot do that. And I think it's very important that that study can highlight and help highlight what consciousness is, how does it work, because it will allow us to understand more crisply what is really human in us.
Another type of technology that I'd like to introduce at this point here, because we're getting, as I said, right down to this nano scale, and our controllability of these nanotechnologies is amazing. So I want to introduce a type of technology called a quantum dot, which is literally a group of atoms, very, very small number of atoms together. This group of atoms here, you can see, depending upon the size of this little cluster, it will fluoresce at different colors. Okay, now this is an important bit of technology which we can use for making sophisticated new devices. This here is the solid-state version of it. This is a quantum dot in a little region of a semiconductor. There's this little space here, and inside that little space there are electrons. And we can tune the energy levels that the electrons have available to them. And in effect, what we can actually do is get away with, throw away the periodic table and we can design our very own artificial atoms. So I want to give you a bit of a taste about that now, but we're going to talk also about the physics which makes this possible. So again, welcome to my course, Nanotech 101. And we're going to talk a little bit about the quantum physics, which is the physics behind these technologies. It's the physics down to the very, very small scales, the world of the atoms, basically. And just to give you some idea again about how small it is, I know we had a look at the width of our human hair, and all the technology is within the width of the human hair. But this is another way we can actually appreciate this scale. So if we have the Earth here and we have a football, the ratio between the diameter of the Earth and the diameter of the football would be the same as the ratio between the diameter of the football and the diameter of a nano object, the so-called Bucky ball, which incidentally is made up of carbon atoms. So this is incredible if you think about these scales and trying to engineer on that level. How do we actually go about doing that? Well, again, we need to have some understanding of the world of the atoms, and we need to have understanding of the quantum physics which is driving this world of the atoms. And the quantum world is probabilistic. Okay, so this is a challenge in terms of our engineering of the technologies on this scale. We're dealing with a world which is run on probabilities. So how do we actually work with that? In fact, you can see a very famous physicist here, Professor Einstein. He didn't actually like the consequence of quantum physics, in that the very small world of the atoms, how can this be possibly run on probabilities? He felt very uncomfortable about that. And he said very famously that God does not play dice. Well, actually, he does. And this is the reality of what we have to deal with when we're designing nanotechnologies on these very small scales. The other thing that we need to have an appreciation for is what's driving the technology. So all the technologies that you have, the most important character, we call it character, that we need to deal with on the nanoscale to get you those technologies that you so love is the electron, which is a negatively charged particle and one of the fundamental particles in the atom. And another property of the electron that we need to understand to build the technologies is what's called a spin, which is its intrinsic angular momentum. And you can think about this in terms of a bar magnet. And there are two types of spin, and we have either spin up or spin down. So you can imagine your bar magnet is orientated one way or the other, and that gives two flavors of these spins. And all the world of the atoms and the electrons and our understanding of it all goes together in the design process and the quantum physics on top of that. And these electrons are very, very sensitive to their environment. And when we're doing the engineering, we need to have a very good understanding of how these electrons basically think, what they like to do, what they don't like to do. How can we control their atomic environment to get them to give us the technologies and the designs that we're trying to create? So it's a very complex thing, but we get a little bit of information from the quantum side. So in terms of understanding these electrons, how they relate to their environment is extremely important. So if you have a material system which is made up of positively charged ions, then the electron which is negatively charged is going to feel that. And because electrons are negatively charged themselves, they will also respond to each other. And in quantum physics, we say that an electron who looks like this is well-dressed. And this is an actual term that we use in quantum physics to describe an electron which feels its environment quite a lot. And if it's not feeling its environment, it's actually looking like this, which is an undressed particle. And of course, these electrons, as I said, they're negatively charged, and they respond to each other, and they do something like this as well on the nanoscale. And this is what's called correlation. So they will move together, and all of this understanding is essential if we're going to design new technologies which need the electrons to give us new nanoscale devices. So if we go back to some of the quantum theory concepts that we have, we go back to this important physicist, de Broglie. And one of the conjectures that he came up with was this concept of quantum physics called wave-particle duality. And so he explained this in 1924, and he was a young physicist at the time. In fact, this was part of his PhD work. And after this, he was actually awarded a Nobel Prize. So that's something to aspire to. It's a pretty amazing feat for a PhD student. So his proposal was that electrons could behave as waves. And again, this goes into trying to get to the root of our understanding of the nanotechnologies and understanding of the fundamental particle which drives them, namely the electrons. So we can have this link between the wave properties and the particle-like properties, which is what de Broglie told us was a fact. And on the macroscopic scale, this is the thing about the quantum theory, is that we don't actually see evidence of it on our scale. It's only when you get down to these very, very small systems on the atomic scale that these effects become quite pronounced. And just to give you an example of that, if we were to calculate the de Broglie wavelength of a ping pong ball, for example, so we can use this equation here, and we can work out that its wavelength is extremely small. So this is to give you evidence that objects on our scale, we don't have to worry about quantum effects, but when things get down to the atomic scale, we do. And in fact, the wavelength for an electron can actually be quite significant, the order of nanometers. And so if electrons have wave-like properties, does it go the other way? Do waves also have particle-like properties? And yes, there is experimental evidence of that. This is Young's double-slit experiment. So light of a wavelength which is of the same order as the slit width here will give a very nice diffraction pattern. But you can think of, what would happen if we had not light, but if we had electrons, and electrons were going through two slits here. So we can heat up this little filament, and we can eject electrons from it, and we can conjecture what would happen. Well, classically, what you think would happen is that an electron would go through either this slit or this slit, and you would get this effect building up on your screen. But what was shown by two physicists at Bell Labs, Davison and Germer, was that what you actually get if you do that experiment with electrons is you get a wave-like phenomena. You get the diffraction pattern coming up. And similarly for light, light is comprised of particles, a fundamental particle being the photon, and Albert Einstein in 1905 conjectured the theory, the so-called photoelectric effect, in which he put forward the idea that light was actually made of particles. And so we have this experimental evidence going both ways. And again, I cannot emphasize this is a very important property to understand when we're having a look at the technologies. So I want to go back to this. If electrons can behave like waves, then what we could do is we could come up with a rudimentary model for an atom. And that rudimentary model would be this box here. and we could confine our electrons into this box. And so you can imagine that each one of these waves here, which are standing waves in this box, actually represent an electron. An electron in the lowest energy level, the first excited state, and the second excited state. And if you remember the image that I gave you earlier about the quantum dots, you'll see that this was also there. So it's important in terms of our creation of the nanotechnologies. And this is driven by a wave equation invented by Schrödinger. But for nanotechnologies and size effects and understanding how size also matters, we can get a very good appreciation from this very simple model of an atom. So if I was to say that the energy is related to this equation here, what was important to understand in terms of the nanotechnology is that there is a size dependence on whether we get atom-like features or something in between, or whether we get something that we can pick up off the ground and have a look at with our own eyes. And so in this example here, if we have a much bigger box, then the distance between these quantized states becomes less. And we move away from this quantum picture to something else. And nanotechnology sort of sits in this sort of scheme here. So basically what we've learned is that we have quantum effects on the nanoscale, that we need to have a very good understanding of the electrons, which is driving the nanotechnology, that we have this wave-particle duality that we can play with in terms of our nano designs, and we have size effects as well. So to give you some appreciation of these size effects, if I have a single lithium atom, then these are the electronic energy levels available for it. As I start to put these atoms together, you can see that these energy levels, they become more of the energy levels, and also the other feature is that the energy levels become a lot closer together. So this is exactly what I was showing you with the box. And we get to a point where we have a solid, and these sort of distinct separations between these energy levels don't really exist anymore. And on the nanoscale, we're sort of looking at this region here. So something which is not strictly an atom is something which is not strictly a macroscopic solid, and something which can, in fact, be engineered and is very sensitive to what we do to it on these very small scales. And that's just a little bit of a summary in terms of Nanotech 101. But what we're really excited about, I suppose, is the applications of this. And yes, this is definitely a reality and what we have to deal with in being researchers in this field. So we're down to this very small-scale design problem. And the question that you might have, after learning a little bit more about the quantum side of it, and having a look at the hair on your head, and realizing that we really do need to be working at that small scale, is, in fact, how do we actually design on that level? Well, in order to be able to do that, we need eyes to be able to see down on this nanoscale. And we use very special instruments, one of which is pictured here, which is an electron microscope, which uses the wave property of the electron. So, for example, if I accelerate my electron to 50% of that of the speed of light, it gives me a wavelength which I'm able to use to be able to see right down to the nanoscale. In fact, I can get atomic resolution with that. That's why I went through and told you all about the particle wave duality and so forth, because we use that to be able to do the engineering, and in this case to be able to see down on those very small scales. So this gives us atomic resolution, and then we get very nice images like this, which is a strontium titanate crystal, And what you're actually seeing there are atoms. So we can use these instruments, these electron microscopes, to do many things. Not only to have the eyes to look down on the nanoscale, but we can use them to manipulate the atoms on the atomic scale as well. And some very intelligent researchers at the University of Wisconsin-Madison, and this is why I've got this object here. This is a Bucky Badger, which is their mascot, which they use for their football matches over there. And what they did is they made a nano version of this little Bucky Badger. And this badger is so small that you can fit 9,000 of them onto the head of a pin. That's how small that is. So that gives you some indication of how we can control things on that sort of level. And these are actually made up of carbon fibers, incidentally. So if we have this level of control on this very small scale, what does that do in terms of leaving open our engineering and how we design with it? And quite a while ago, in 1959, a very important American physicist called Richard Fineman gave a prediction in terms of what he thought this might look like. And of course, they didn't have the ability to do it then. So this is definitely a prediction. And he said, but I'm not afraid to consider the final question as to whether ultimately in the great future we can arrange the atoms the way we want, the very atoms all the way down. And he said this in a popular lecture that he gave. And in fact, this is what we can do today. This is our level of control that we have. And from there, we've gone to develop all different types of nanotechnologies. This is probably one of the earliest examples. This was in the late 80s. IBM researchers using a special type of electron microscope to grab atoms, in this case xenon atoms, and to move them around on a nickel surface. And they were able to spell out the words IBM with that. We've since moved on from there to various types of nanotech objects, going from layered systems, which is shown here, so very thin atomic layers, in this case cobalt with a copper layer sandwiched between them both. And this particular structure here can be used to manipulate the spin, which I told you about, that is the intrinsic property of the electrons. And in doing this here, we can apply an electric field to this system, and we can turn on and off how the electrons are aligned across the layers. And what we have invented with that is a memory device, which is used, it's called the GMR effect, and it's used in your iPods. So this technology has come to fruition, and it's actually something which is used in your devices now. We can control how atoms grow on different surfaces. So this is literally a picture of cobalt atoms on a platinum terraced material. And as I was saying, we can arrange these atoms as well. We can put them in different types of structures. We can create very, very small atomic scale atomic clusters. And we can create these devices which I have alluded to at the beginning of the lecture, which is this quantum dot. And in this quantum dot here, we have this effect. We can literally, by changing the width of this little space here, we can control these energy levels, we can control the distance between the energy levels, and we can literally get rid of our periodic table of elements and create artificial atoms from this. And that's what we have here. So as a function of the size of this system, so as a function of the size of the box, we're changing the difference between the energy levels, And in doing so, if I excite an electron from here to here and it re-emits and I get this color, if we change this width of the box, if we change the size of these particles, we then change the difference between these energy levels and we get out different colors. There are other types of applications of these nanotechnologies, and because I've spoken to you about the atomic clusters, I'd like to play this little video which will show you some of the really exciting applications of magnetic cluster systems.
The centerpiece of the MagForce nanocancer therapy is the nanoparticle, consisting of iron oxide. The particle is covered by a patented coating which ensures a good stability and division of the iron oxide particles in the tumor tissue. It additionally supports the process by which the particles are absorbed into the cancer cells. The small size of the particle is decisive for the therapy. The diameter measures some 20 nanometers and is thus 500 times smaller than a red blood cell. 1 milliliter of the particle solution contains nearly 17 trillion single nanoparticles. This high density makes efficient treatment possible. At the beginning of the therapy, the nanoparticles are injected directly into the tumor. The tumor in this particular case is a glioblastoma, a malignant brain tumor characterized by aggressively growing cells. On the microscopic level, the healthy cells can be seen on the left and the tumor cells on the right. After being injected, the nanoparticles spread out in the spaces between the tumor cells. The patient now enters the therapy device in which an alternating magnetic field is produced which is of no danger to humans. This field affects a 100,000 times alternation of the magnetic poles within the particles per second, creating warmth which is precisely regulated from outside. The warmth forces the particles into the spaces between the tumor cells, which makes it easier for them to be absorbed into the cell. This application is repeated and the thermal effect increases visibly. The particles begin to oscillate, causing the cancer cells to die either from active self-destruction or from swelling until they literally burst. Tumor growth is stopped and the destroyed cells as well as the nanoparticles are discharged by the body in a natural process.
Okay, so that gives you again some indication of the applications of the nanotechnology. Nanotechnology these days is not just restricted to physics, it's not just restricted to engineering, it's moving out now across many different disciplines, chemistry, biology, all working together to create something like this, which is an amazing revolution in terms of potential treatments for cancer. And this is a bit of research that I'm also actually involved in as well in terms of designing these very small nanoclusters and optimizing their properties to be able to give precisely the amount of energy when it's interacting with an external magnetic field to be able to kill the cancer cell tumor. So there's quite a lot involved in terms of the design process of that. But it's not just as I said, chemistry, physics, and engineering. Again, we're starting with the biology, and some very interesting ideas are being put forth in terms of how we can use biological systems, for example, viruses in this case, to be able to design new technologies. And this sounds very futuristic, but it's something which we're doing at the University of York. And I've got a little clip here from somebody who's also doing this at MIT.
Imagine a world where car batteries are assembled by biological organisms. They are non-toxic, biodegradable, and very powerful. Step into the world of Dr. Angela Belcher. She walked on this beach during her college years at UC Santa Barbara on the few days when she wasn't busy getting degrees in chemistry, biochemistry, molecular biology, and electrical engineering. This is where she got her inspiration for a radical line of research that could change batteries forever.
So when we're thinking about how to make new technologies, we're going to look at it from a very new perspective. 500 million years ago, when the environment of the ocean changed, organisms that were soft body organisms didn't make hard materials, didn't make shells. But through selection pressure and through changes in the chemistry in the environment, they learned how to make materials like shells.
Only a multidisciplinary mind like Angie Belcher's would look at that and think this.
And we said, wow, if organisms could make shells, I wonder if we could get organisms to make batteries.
The idea of teaching organisms to make batteries seems out of this world. But Angie Belcher has found a way.
The reason that it's such a special structure is it's based on nanotechnology.
Nanotechnology refers to one of the smallest units of measurement, the nanometer, a billionth of a meter. Like the abalone shell, Angela Belcher wanted her nano batteries to harness the power and perfection of biological systems.
I isolated the proteins that are involved in making the really exquisite structure of the shell. And by looking at the periodic table, I started thinking, well, what about all these other elements? Can these same proteins that work for shells, can they work with other kinds of elements? And in fact, it was pretty amazing they could work on other kinds of elements. So what we had to do was pick an organism that was easy to manipulate and could be propagated on a very short time scale, so we picked viruses.
The virus, it usually makes you think disease, but in Angie Belcher's lab, it's a hard-working green machine.
And then we actually start with about 1 billion viruses that are all genetically identical to each other.
Even though the viruses are identical, they have minute differences, the same way identical twins can look and act differently. What Angie Belcher and her students need to know is which of these viruses will bond with a metal oxide material. That's what makes them conduct electricity. Out of 1 billion, only a tiny handful will succeed.
So these are the winners. These are the ones we're going to keep and test to be able to grow our electrode materials. We take those and we isolate them.
These winners are taken for a ride down to Dr. Paula Hammond's lab. Here, they'll work 24/7.
We can build very, very thin films simply by taking one material which has positive charge along it and another material which has negative charge.
The beauty of this virus is that if you put it near a sticky surface, it begins to organize itself in rows. Like bricks and mortar, the viruses stack themselves. Pretty soon, they've built a solid plate. This is the plus side of the virus battery. On the other side, a different virus builds the negative plate. To finish off the battery, tiny wires are attached.
And this is the final product, an ultra-thin, ultra-lightweight, fully water-based virus battery. This is very exciting.
So if that to me is completely amazing that we can use viruses to build these templates by which we can grow and self-assemble material systems. And if you remember when I was talking about the graphene system, one of the things I like to do is we'd like to have control on the nanoscale in terms of the structures that we can make out of that single atomic sheet of carbon. So you can imagine that we have nanoscale scissors and we can go to this carbon sheet, which is only 1 atom thick, and we can cut out some very, very small nanoscale structure. The issue with doing that from going from the top down is that our scissors will not get us a perfect system in terms of how we cut it out, in terms of how the edges of that structure is. And nanotechnology is very sensitive to what we have in terms of structure or atoms and what the general environment is like on that scale. So one alternative is to see if we can get these carbon systems to come together and to self-assemble and to use our understanding of chemistry or biology to get them to assemble into perfect little structures. And so that is really the level of control that we're trying to achieve. This is really the next step in terms of engineering on the nanoscale. As I promised, we've come to a point now where Nanotech 101 should have given you enough information and understanding for us to be able to create some nanotechnologies right here. Who believes that this is possible? Do you think that we'll be able to do it? Okay. Are you up for it? Okay, good. So what we're going to need is we're going to need the quantum mechanic. And so I thought I would play the role of quantum mechanic. And I've got my overalls here, which I'll just hopefully quickly get into. So you can see we really do take this seriously. Almost there. Okay, is that convincing enough? All right, so I'm going to play the role of the quantum mechanic. Oh, the other thing I'm going to need is my spanner. So I've got the spanner. We're going to need some atoms. Let's see, do I have those available? As it stands, I do. So I have 3 atoms, which I'm going to put down here. What do you think's the missing bit in this? What was the emphasis on in the talk today? What was driving the nanotechnologies? Oh, electrons. Okay. Let's see what we can do about that. So that's what we've come so far. We've got the nanosystem, we've got the atoms. Now we have to select the electrons. And I have 2 electrons here. And I need 2 volunteers to help me to build the nanotechnology. Okay, got 1 person at the back. If you can get out. Anyone else? Yes. So let's give our electrons a big hand. And your name is? Ben. Yeah. Hello, Ben. Would you like to be, and your name? Amber. Amber. So do you have any preference as to whether you're going to be spin up or spin down? Spin up. Okay. So Ben's going to be spin up, Amber's going to be spin down. Now, as the quantum mechanic, I get to impose on you guys the quantum rules. So the first thing I'd like you to do, and you've got to remember, you've got to really get into the character of this because you're negatively charged particles. Okay, so let's sort of just start off by asking you a question. How do you feel about being close to each other? From the perspective of electron.
Repelled.
Okay, so do you feel happy or sad? Okay, so we need to show the sad face. Yep, brilliant. But now what I'd like you to do is I'd like to invite you both to come into this nanostructure that I've got, this 3-atom system. And I'd like to invite spin down to be here. Thank you. Right on the atom. Perfect. And spin up, I'm going to have you here. Okay, and again, like I said, this is serious. This is really exactly what I do in terms of my research, believe it or not. I build these nanostructures, I use quantum theory to do it, and then I get to understand how the electrons feel and try and find ways in which I can manipulate the nanostructure to get the electrons to do what I want. That is, to give us the nanotechnologies. So I'm going to ask you both, how do you feel at this point? You feel all right because you're as far apart as possible from each other, so we should have our happy face. Excellent. A round of applause for that. Excellent. So, Mr. Spin Up, Ben, I'm going to destroy you from this state here, and I'm going to create you again here. So if you can just position yourself there. And remember I was telling you about the Schrödinger equation. Now, this is exactly what we do in the Schrödinger equation when we try to model these nanosystems. And I'm going to ask you both, how do you actually feel?
Yeah.
Yeah, a little bit uncomfortable. Okay, so somewhere between happy and sad. Now, the thing is, in terms of the degrees of freedom, I can actually destroy my spin up here from this atom and recreate my spin up here in this atom. So if you move across to where amber is, a little bit squishy on the atom there. How are you both feeling? Really, really sad. Okay, so let's give our electrons a round of applause. And now I'm going to show you how that actually builds nanotechnology and how we've actually created it right here today. So thank you both very much. I'll take the electrons. Okay, so we had our spin up and spin down electrons, and I positioned them inside this nanostructure. So this is an actual calculation in terms of what I call the percentage happiness for my electrons. So if we have a look at this here, so even though they said that they were feeling slightly uncomfortable, in terms of the probability of whether we would get them in this particular configuration, the probability is actually highest, because it's not only how they are feeling next to each other, it's actually also the degree of freedom that these particles have. So here we've got our particle, and this particle can move from here. It's a spin-up electron. It can move from here, and it can move there. So it has some degree of freedom to be able to move within this teeny tiny nanostructure. And because it has this degree of freedom to move, overall, this particular type of configuration ends up being the most probable, or the electrons tend to be most happy in this configuration here. If they were on the outside, so even though they felt more comfortable being as far apart from each other as possible, if you think about it, we have a little bit of an issue. Because the next thing, in terms of the degree of freedom that they have to move in the nanostructure, is that they would end up both being on this center atom. So that's why, in terms of the quantum physics, this particular configuration doesn't weigh as highly as this one here. And this one here, they really didn't like that at all, did they? They didn't like being on the same atom, having spin up and spin down. And in fact, that costs the nanostructure a lot of energy. So that's why the measured probability of electron happiness is quite low for that particular configuration. But you might be asking yourself, how do we get nanotechnology from this? Well, if we take what's called a superposition, or if we have a snapshot which looks at all of these types of configurations, and we have one snapshot which takes them all into consideration, we would get something which would look like this. So a structure which has alternating up, down, and up. If we then put a spin up to be a 1 and a spin down to be a 0, what do you think we have invented? We've invented exactly a quantum memory system. So yes, indeed, we did build the technology here today. And again, thank you very much to both of my electrons for helping out. So just in summary, I've spoken a lot about nanotechnology. I've spoken a lot about quantum theory, which is driving it. And we did meet the aim, I hope you will agree, of building nanotechnology here today. So I hope you've all enjoyed the lecture, and maybe consider finding the nanotech in you. Thank you very much.